today's talk, the theme of it comes from a few times in the past year I've been giving talks because of certain trends in computing that have become on trend. So for example, Internet of Things, cyber-physical systems and so on. And in these talks, what I've been presenting to quite high people in the government and so on and so forth. And they all come with, well, IoT, very important, very important. And then the one common thing that I saw last year was that they'd come to me and they'd say things like, yeah, well, actually it's all very important and the kind of things you're doing is very important. However, it's all in the data. The data is where it really lies. That's where the real important research is. And so if I was a little bit more insecure, I might have been offended by those marks. But I wanted this talk to show why just looking at the data and pretending, and note I say pretending IoT, sensor-based systems and cyber-physical systems are all okay, just like your phone or your laptop, is quite dangerous. So that's what this talk is about. So we're starting to see a movement in the world towards more instrumentation of infrastructures, homes and so on, and you're starting to see that yourselves. And the usual reasons that we typically instrument systems with sensors is to try and understand what's happening in that system at a level of granularity that's lower than what we can do today. Now, typically to do that, we employ many mechanisms, and one mechanism is to use sensor-based systems. And to allow us to be able to retrofit these sensor-based systems into environments like, for example, up on the top of these guys up here, or environments that are difficult to get at, it means we have to have certain technological aspects to them. And those could be that the system itself is retrofittable in terms of you don't have to run wires to it. And that has implications for the power to the actual device that's sensing, but also how it connects to the world through the radio communications. And so the use of these kinds of systems, regardless of what you call them, because I interplay all those different words constantly, depending on who's trying to fund me, I try to use whatever. So you've got sensor-based systems, obviously, in the more smarter cars, that's an electric car. These systems, you can have these onto a smart grid, and the smart grid allows us to understand what's being pulled off our harvesting systems and how we can optimize that. So typically we get these sensor data in to allow us to do a number of things. Mainly, we want the system that we're instrumenting to be efficient, to address customer demands many of the time, to optimize for costs, and also to look at the sustainability, the long-term operation of that system. So for example, asset management and prediction of where that asset is going to fail, and then how to build a production so that we can basically fix that in time or order parts in time and so on. So we're starting to see that a lot more, and that's the kinds of systems that I look at. I tend not to look at systems where, we're talking about smart homes as such. I tend to look at the big belt and braces kinds of infrastructures, smart cities, that size of things. So what I'm particularly interested in, because of its nature, is critical infrastructures, as I've just said. So what I would describe as critical infrastructures are structures that we use throughout our day-to-day lives to allow us to have a comfortable and long life, essentially. And things that I would consider as part of that are, for example, precision farming is one example of that. Basically, we want to be able to get more out of the land because we only have so much land, arable land, for example, on the planet. And if we have the predictions of the numbers of persons that we expect to have by 2050, then we're going to have to be an awful lot cleverer with the use of that land. And you're going to see a lot of conversations about precision farming. So there's an opportunity here to better understand the land, the thing that you're growing in the land, for example, and its needs down to a very fine grain level. Therefore, you do not have to waste resources and over-provisioning things like fertilizer or feed or water in particularly is very important. So you can do this nice tailoring exercises. Likewise, the other thing I tend to work a lot with is water distribution networks. As you probably know, what fine water delivery companies many millions of pounds if they do not attend to leaks. So we need to be able to better measure those leaks, predict those leaks, and fix those leaks fast as well. And this is very important, obviously, in countries where water is highly scarce. And you can get the gist of the kind of thing that I call the critical infrastructure. It could be a massive manufacturing plant that wants to be adaptable to its manufacturing, so it's Industry 4.0, or it could be aspects of the city. So it could be, for example, the transport network. We want to be able to understand, you know, how the rails are working, if someone's walked onto those rails, how we can efficiently detect if there's going to be a problem with them, and so on. And there's so many things we can do with sensors at that level. We can do what's called blue-greening the city to make better use of watering the plants and the trees, which in turn impact our consumption of gases that we don't want to consume, and so on. So you get the gist, you get the gist. So these kinds of systems typically cover geographically wider areas than your chemical plant, okay? And so that makes them slightly different. And a lot of the time they're providing services for us, and the companies or the industrial infrastructures that own them don't want to really have to have a massive added cost added to it in terms of being added the sensors and so on. So the sensor systems themselves have to be fairly low cost but effective. So that's what the common sort of theme is for the talk today. So this leads us to a set of challenges from a computer science perspective. I'm in the Department of Computing in Imperial, but I'm quite odd in that I could be easily in electrical, so I kind of span both. So the main challenges that we see in these kinds of systems revolve around costs, scale, and trust. So the costs, as I mentioned earlier, as a computer scientist, sometimes when we're doing research, we go into the system and we think, okay, we're going to make this work properly, beautifully, whatever. But in our end of computing, we have to bear in mind the cost, because the kind of computer system that we're talking about tends to be in the frugal end of computing, low cost, small microcontrollers, so on and so forth. So we have to look at low-cost sensing and alternative ways of getting data, which could involve participatory sensing, where, for example, you've got users or users' phones and so on in part of the sensing regime. And I'll talk much more about that later. Scale is a big issue in these kinds of systems. That's in terms of the numbers of things that we have out there doing the sensing, and where we have actuators, we have to control those as well. And the numbers of those, as they start to scale, start to have different behaviors. And this is what I also want to mention. So we want to be able to ensure that no matter what the scale size of those are, and scale could be numbers across a large space or lots of them in a smaller space. So the density is important there as well. And they have to all get equal opportunity to operate, should that be the policy of the system, and so on. So we have to understand their interconnections, their ability to intercommunicate, collaborate, and produce whatever's expected of them. And of course, the means of communication is typically over wireless networks. Therefore, we have to be very cautious of not consuming too much of the network capacity, especially important given that the air itself is carrying all these communications, is competing with other sources of communications and networks and so on. And then finally, there's no point in pulling data off the world if you can't trust it. So we have to look at the integrity of that data, how accurate it is, be able to report what precision and so on it has. And then we also want to make sure that it's secure, so that it's not lying, it's not compromised or stopped in some way. And typically, one of the ways that my group has approached this problem since we've started 18 years ago is to look at very agile, very self-adaptive and decentralized computation. So there's different issues that come along when you start to decentralize the system, in terms of the system being very good at not falling over if one component of it dies, but on the other hand, it's not necessarily running at its optimal constantly. So we have those trade-offs. So I'll take each of the challenges to give you a sort of run-up as into why cyber-physical interactions is important for these kinds of systems. The first challenge is to do with the very fact that we're talking about frugal, low-cost systems, and they're typically exposed to real-world environments. And even when they're well-cased, they're exposed to real-world environments. So they're typically low resource, which means, on the whole, we can't run large ML algorithms or all sorts of security algorithms on them, because they can just barely run their operating system, which is usually not a full operating system, and the application that they were designed for. There's not much room on these devices. They're fairly flaky. You can easily disrupt them. And what we've tended to do over the years is to just accept that flakiness, because there's not much else we can do. So the low capacity, to give you an idea, this is I think it's a Berkeley moat. It's basically, we're talking in terms of, let's say, flash memory, it's like 512K bytes. It's tiny. We're talking small systems. We're talking about what was basically the systems that people played games on in the 1980s. So to overcome these problems and taking the assumption that these systems will fall over and misbehave, we've tended towards building algorithms and protocols and so on to get these systems to work kind of in a bio-inspired way. That is, for example, where we imagine them to be like dumb bugs that are able to communicate and interact and collaborate to do system-wide optimizations. So we'll take, for example, so this is a firefly. In our systems, when we want them to communicate, because they're typically battery powered, we put them to sleep when they're not needed. And then we get them to wake up, so they come up, and we want them to do some sensing, for example, and then typically after that, we want it to communicate what it's found. Now, to do that, there's a number of different ways to do it, but one of the ways that we have found has been very useful is to what's called multi-hop the data across all the different other devices in this space. And one way, so basically when we do that, so the system basically goes to sleep, comes up, does its sensing, and then wants to form its network usually, and then start to send the data to wherever it needs to go. Now, the problem is with these kinds of low-end systems is that when the system goes to sleep, it may say, right, I know I have to wake up in 2 seconds' time or whatever number of seconds' time, for example. It may wake up in what it thinks is 2 seconds' time, but its neighbour may wake up in what it thinks its 2 seconds' time is, and they're not the same 2 seconds in the world, okay? And so what happens is the system is unable to form networks or carry out other collaborative tasks, for example, share data for aggregation or communicate to understand the data better and so on, because one node is still asleep while the other's awake. Now, sometimes we play around with that to keep the nodes awake slightly longer than they need to be to accommodate for this. And this is typically caused, as I said before, by numbers of different parts of the world. So basically, the node itself, the oscillators inside it, the device itself, they're relatively flaky, so they're not counting time correctly. But other things can impact that. For example, what we have found is that the temperature of that device in a given space can also affect its oscillators. Therefore, it may not come up at the same time. So we've got the effects already of temperature in being able to make sure that these systems work. So we typically build it with those kinds of problems. And the trouble is, in these kinds of systems, we don't know all the problems it's going to have. Therefore, we have to imagine the worst cases in many occasions, and from that then build our algorithms, our protocols, and so on. So based on nature, nature's very good at that, at basically building some sort of collaborative system that doesn't use an awful lot of power in its own right. Like, so for example, ants don't use individual power, but the colony is where the actual optimization happens. However, the difference between ants and our systems are that our systems can't scurry around looking for food. So we have to overcome that problem somehow. Now, traditionally, our systems were battery powered, but moreover these days we're starting to look at energy harvesting solutions for them. And there's a number of sources of energy harvesting. So for example, we can have piezoelectrics, we could have vibrations, we could have solar, so on and so forth. And basically what we can do from that is then we've got this energy harvesting opportunity. We know what the application needs. We also know what the computer system needs. There's two things going on here. We've got the application and we've got the computer system itself, the interaction between all the devices to do things like routing. And we know what the requirements for all that is. And somehow we have to maximize the quality from the requirements to the energy opportunity. So typically we run a lot of optimization at this point to try and minimize the distance between the quality that's required and yet maximize the energy that we've got. And so, for example, what we've been able to do using our energy neutral operation algorithms is to even prove, for example, that if we have a solar paneled device, we can keep it alive overnight. And so obviously this is a form of budgeting the energy in the system, and something has to give, and typically that's the sleep-awake schedules, sampling times of sensing, and all sorts of different things like the power going into the transceiver, which is sending the data. So we play with all those different levels until we get our optimal, and then that optimal has to last over long durations of time. Now, a lot of these people haven't realized that when they put energy harvesting systems onto the devices, they just assume that the energy, the battery itself that stores that energy coming in, will last forever. The reality is, as you know from the use of your mobile phones, is that they only last a few years, typically. So what we have to do is, if we're going to have a energy harvested storage battery that only lasts 3 years, well, sure, we may as well just stick a big battery on the thing, a big normal battery, and not worry about it. So what have we been doing? So we've been looking at this in much more detail. We've been looking at the physics of the battery, the physical aspects of the battery. And what we have found is the way we run the code, the way we schedule the code can actually impact that. And therefore, we've taken that into account. And what we've managed to do is double the lifetime. So if it was a 3-year battery, it's gone to 6. But moreover, we've been able to show that we can achieve 10 years, which is typical for critical infrastructures, 10 years lifetimes. So, and that's not by changing the chemistry of the battery. That's by understanding the chemistry of the battery and reconfiguring how we run our systems. So this is the cyber-physical interaction and how the advantage of understanding the physical behaviors of the computer system and its environment can actually make the system run better. And more recently, we've started looking into alternatives. This is quite in its early stages, but I thought I'd mention it, whereby we can, basically the TV towers that we have across London are out broadcasting, so that's TV white space essentially. And what we can do is pick up the energy from that radio signal and power up our nodes. So we're looking at how we do that, but again, you know, that's just getting the energy into the node. We have to make the best use of that energy, given the cycle of its operation, and make sure that we are able to fulfill the application that that device is required of it. So that's energy. So you can see we do a lot of work on energy, because that's our Achilles heel. So we're quite bounded by the physical world as well in our systems, and I've hinted towards this as well. So this is our other Achilles heel. Now, so typically you will see Gartner, et cetera, they're predicting all these billion, squillion devices in our environments, and especially in, for example, cities. And these devices will all be competing for the air as a means of communications. So, for example, the 5G people have been working on this for some time, and they've been trying to look at different ways and mechanisms to get the best out of maximizing the capacity of the air, essentially, if that's what we're communicating over. And we are similarly looking at this as well. So what we try to do is we try our best in our world to not take away from, for example, the airtime that emergency services would use. Or, in fact, even your mobile phone is considered more important. So we try to squeeze our way in amongst all the bits and pieces within that so that we can get our data up as accurately and as reliably as possible, but without impeding on other systems that also share with us. And so we have a number of pieces of activity within that. So one of the types of communications that we're frequently using these days is low-powered wide area communications. That's basically not like Zigbee and so on that we used in the past, which would cover a number of meters. We're talking about multi-kilometer distances. The advantage is that it's still low powered at these multi-kilometer distances. The disadvantage is that data rates are very, very slow. Okay. And one particular communications type we've been looking at is a protocol called LoRa, if those of you are familiar with it. And LoRa has different ways of playing around with its operational parameters. So, for example, it has spreading factors that have impacts on the speed of the data and on the distance of the data. And so we try to optimize, given the applications, given the urgency of the data that's coming off, we try to optimize how we can ship that data back to where it's needed to be, playing with those parameters. So we do that a number of times. So, for example, we're looking at putting, traditional what's considered NOMA onto LoRa, for example, and there we're balancing the needs of the application, the frequencies that we can use, and the power that we can force into the antenna, given our power budgets to keep the system alive over long durations of time. So you can see, again, we're playing around with lots of optimizations here effectively. But it's not traditional communications that we've just focused on. We've looked at ways of borrowing what already exists out there. And one way to do that is called opportunistic networking. So can you imagine that you have a little app on your phone, and in the background it runs, it doesn't bother you, it runs in the background. And what it's doing, for example, if you're walking through a park, it's picking up my sensor data from the park, jumping it through your phone to someone else's phone, to someone else's phone, to free Wi-Fi, where that happens. So that basically I get my data back. I'm not taking up much more of the capacity, but I'm making use of what already exists. Another advantage of that is it means, like, for example, a city or a park, for example, don't have to put an infrastructure in there. Therefore, if they don't put an infrastructure or communications infrastructure in to allow that data to come back, they don't have to maintain it. They don't have the costs and so on. So it's basically, it runs in the background of your phone. Now you're saying to me, Julie, that's problematic, isn't it? And I'm thinking, yes, it is. One is, why would you ever give me your phone, okay? And so we've looked into things like incentivization techniques to incentivize the use of the phone. And we've built incentivization techniques at 2 levels. At one level, we're looking at the accountability of the individual providing their phone. So if we use much of their battery, it's accountable. If we use, say, for example, the Wi-Fi, it's accountable. It's taking a lot of their battery also. If it's just multi-hopping through Bluetooth, we can account for that. And they're all different rates of accounting. And what we can do is we can prove that we have a fair system that balances out the use of your phone to what the costs were, and therefore the recompense that you get. However, what we don't do is, because I don't do human psychology or anything, we don't equate that to the reward, essentially. We don't say, right, that is brownie points in a game, or we don't say it's actual cash, though we have done some Bitcoin stuff to that end. We don't say that it's, stars in a chart of something. We don't do that end of it, right? So we just make sure that it's fair. It's fair and it can't be hacked, right? We also make sure that our applications running on this phone are private, so that I don't nick your data and you don't nick my data. So we make sure that happens. And that has a cost, obviously, in the phone too, because that's basically wrapping the application away and isolating it. So we have all those kinds of things. And there are ways of trying to overcome that very physical bounded problem of getting data across a space, given that we will have capacity problems if we have as number of nodes as predicted. But I want to take this further. There are other things that impact on these kinds of systems. And the first one, I thought I would illustrate it using a project we did back in 2012 with Reading University. Now, our remit back in 2012 was to take this beautiful field and underground sense across the whole space using what's like a grid of sensors. And they basically are embedded there. No antenna can be above ground because there's animals that feed on that. People walk across it. The only thing I was allowed was a few base stations up in the trees out of the way, but everything is underground. So we had to dig it all underground. It still also had to be low powered, and it had to have a small form factor. So we're talking about small end computing systems, because that would defeat the purpose. This is a scientific field of interest, and they're very curious as to why the particular plants mixture there, which is unique on the planet, is why it's there. So that's great. So we had it up and running, summer of 2012. It was up and running. It basically went to sleep, woke up, sensed, measured soil moisture content, blah, blah, formed its network, relayed the data across to the base stations. Brilliant. Except winter, it's a floodplain. It looks like this. And those of you who know a lot about low-powered radio communications will realize it's not really easy to get it through water. Water's a nightmare. You have to go into sort of ultrasound to get anything through water. So we had a real nightmare with this. So what we started to do then was we updated the system to read the quality of the network availability caused by the water in the soil. And if we thought we were not being able to form a network, we would let the system sleep for longer and start to compress the data instead, which worked. Which meant, though, we basically, at the worst parts of the year, they go into hibernation, essentially, just waking up and sensing and storing until spring comes, and then they dump the whole lot down. And that's okay for those kinds of scientists. That worked well. Now, what happened was that we started to look at this, and we found that the radio itself was able to determine better the conditions of the soil than the very expensive £1,000 a piece soil moisture sensors. Okay, and we started to think this is ridiculous. Our radio, which is like 25 quid, can read that better. And we started to investigate that, and I'll show you in a few slides' time where that has gone. But I think this is the perfect example of cyber-physical interaction and why we have to be conscious when we're building these systems. Okay, so what we've got here is a water distribution network. Now, currently water distribution networks consist of pumps to pump the water around. A lot of them are gravity fed, so they try to minimize the number of pumps and therefore the energy to run that water around a space. They typically have large trunk mains, and then off that is branch mains, and then off that is smaller. It gets basically, it's a graph essentially. And then you've got what's called a basic unit. It's called a DMA, district metered area. And that's the lowest unit of control, essentially, where they can have valves. Now, that's today. So the pipes are pretty passive. If a leak happens, it's usually detected when someone phones rather than when a computer system or the SCADA system, for example, says that something has happened. So it's quite a delay, and then it takes a long time for anyone to fix it, usually a number of hours. And it costs an absolute fortune to fix. So that's today. Next generation water networks is to try and move it to something like we have in the internet, which is more of a water switching network, okay? So where we have lots and lots and lots of sensors out there, so they can't be expensive and they have to be easily retrofittable. And moreover, we have to have lots and lots of actuators, valves, cutoff points, and so on, spread out so that we can do things like, for example, we can, if there's a failure here, we can allow the water to come around here and not come through here and actually leak out further and so on. So we've got all of that, and it makes it much more flexible. It allows us to meet customer demand better, and it allows us to save water, which, as I said before earlier, it's very, very important. Right, but here's the deal. The water system itself, from a hydraulics point of view, has to be optimized. So if you've changed it from this passive water network to a more optimized switching network, we still have to take into account the physicality of the water network itself and maximize it so that it serves customer demand. It doesn't put too much pressure down the pipes because that shortens the lifetime of the pipes and so on. So we have lots of constraints. That's the physical system. Meanwhile, I have a computer system. This is a colorful bit. Computer system that has valves and has sensors and has relays and so on and so forth. And again, I have to make sure that that system will last the 10, 15 years that I've promised. I have to make sure that it delivers data to the right place at the right time. I have to make sure that it does, the quality of data is peak for that sort of thing and so on. So I have a whole big optimization at that level. But here's where the interaction happens, okay? Now, if I make a decision based on, say, for example, the sampling rate of the sensors in the computer system, that has implications as to how the physical system is represented in the machine, which has implications on how the machine controls the valves. So, for example, if that data comes in as a delay, then the state of the water network is not correct, and therefore the system is reacting to a state that does not exist at this moment in time. And that also holds for messages getting back down to the actuators. So we have a nice control problem there, and delay is obviously a big deal. The second cyber-physical interaction is, for example, if I want to slightly overshoot to bring the system into a level of stability, what I will do is I will open a valve, but the trouble with that is that it causes transients in the water, and again, that shortens the lifetime of the pipe. So we've got a cyber system interacting with the physical and hurting the physical system as such. In this particular system, I have a further interaction. My sensor nodes run off harvested energy, which is run off the vibrations of the pipes themselves. And therefore, I'm actually getting energy in the system based on the differential of the movement of the pipes. And therefore, I can do things like, for example, force the pipe to shake a little bit more to ensure that I've got the energy in my system to elongate its lifetime. But again, if I do that and it causes a wave, then I've shortened the lifetime of the water network. So we've got all these interactions here, and I've just mentioned a few. These are the most obvious ones, but it's two very different systems so tightly coupled. And the truth is we don't know how to make sure that we give guarantees in this kind of situation and so on. So I hope you get an idea of why looking at these kinds of systems at that level is important. It's not just a bunch of systems pulling off data and then all the hard works in the analytics. If that data is not coming off correctly, it could really ruin the system. Now, back to the little story I told you before of the floodplain. We'd found that the antenna was able to tell us more about this physical environment. So the digital antenna, well, it's a physical antenna too, told us more about the environment. So we thought, well, let's play with this a bit more. And so we built what we now call Cognizance. And what Cognizance does is there's basically a room full of machines, and it has a transmitter and the Cognizance receivers. And what it does is it fires basically a radio frequency signal through the machine, and the machine munges that signal, and then we record that back up in the Cognizance receivers. The Cognizance receivers are tuned to individual machines, so we can identify where the machine is, and then we can start to identify deviation from the norm in that machine and start to watch it deteriorate. So here is an example of where we have seen something that was causing us a problem in the physical world. We're now turning it on its head, and we're using it to be able to measure the physical world as a result. So this is the positive story. We've also used this when we were testing it in the lab, for example. We could see people swinging their legs. We could see your heartbeat. We could see your heartbeat from in a different room, and so on. And we're now using it in precision farming, which I'll talk about in a few slides. So that's a positive thing where you harness the cyber-physical interaction to make a better thing in the end. Oh, that's what the motional signature is. So the motional signature, you can isolate the bits that you're interested in from the stuff you're not interested in because of the frequency. So as I said, slide before last, the thing is we don't really quite understand that cyber-physical interaction in terms of guaranteeing that the computer system will be providing its services correctly. And we also don't know exactly how that impacts on the physical system and so on. So I was lucky enough to get funding from EPSRC with Muffy Calder and a bunch of other people to do this very thing. So we're starting to look at that. We are trying to understand how we can definitely, under all that non-determinism, how we can make assurances about what the sensor system's supposed to do in different dynamic environments. And what tools, what methods and what approaches can we give. So we've got, for example, Muffy, as those who know Muffy, she does formal verification, whereas I'm a systems person. So we're trying to work together as two different types of people to try and see how we can actually elicit some tools, mechanisms and ways. But the interesting thing for me is these guys come from the verification of code backgrounds, that's software. And I'm coming up maybe from the bottom up. I'm in bits of hardware and software as well, obviously. And so I want to somehow bring that physicality into it. And I just, if anybody has an idea, I'd be very happy. So, things like, for example, we look at the temperature. If the temperature changes, as I mentioned earlier, the oscillators don't work, therefore the timing in the system doesn't work, and it has problems with synchronization. If we don't get the full voltage in from whatever we're harvesting our battery, say a battery's starting to deplete and the voltage starts to go down, we start to see implications for the sensor. The sensor itself starts to lie. And then the noise floor on the radio system starts to get peculiar, which means we think we have a nice clean piece of radio between me and my neighbour, but we don't. And that's all because I'm not getting enough energy into my battery, from my battery into my node. And there's all these interactions of all of those things. So we're starting to see lots of interesting things. Another one is the frequency of the radio changes as the temperature goes up as well. So it's all these crazy things. And we're somehow going to have to model this so that we can start to give the guarantees that we need to with regards to these systems and the data that's coming off them. Another aspect that is now something we can no longer ignore is the security. If we're sticking these out on critical infrastructures, and they're running those critical infrastructures, they obviously have to be reliable, but the other side is they have to be secure. So working with Petrus and a bunch of other people, including Cisco, we've been looking at identifying where the sort of map of issues regarding security are, and how in our tiny little computer systems with very little extra resources, we can manage to have them configure themselves so that they can protect themselves in some way. And for those of you who are interested in data analytics, one way that we've been doing this is that this computer system itself is monitoring its own behavior, and when it starts to deviate from its own behavior, it starts to then signal that there may be a problem, there may be a malicious intrusion, for example, or the system may be jamming, and I can reconfigure my system to change frequency so it won't jam on that same frequency, and so on and so forth. So a node tampering, for example, that's another anomaly that we can look at, and that the physical system's being moved, so we know somebody's been doing something. Now, we haven't covered all of these different attacks as yet, but the aim is obviously to cover them. But as you can imagine, if I have a way of mitigating all of those attacks, plus my application running, plus my normal, routing system, operating system, blah, 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 running in these tiny little systems, it's going to be an awful nightmare to try and schedule them. So we have to look at new ways to do that to give those guarantees as well. So what are we doing in Alan Turing Institute? Because I imagine some of you would be interested. The themes of the work that we're doing here are the following. So we're looking at, as I said, sustainable infrastructures generally. So that's those infrastructures that I've talked about earlier. We're looking at control and rethinking control in the context of these kinds of systems. And we're looking at the fact that these are in changing environments. How do we learn from the data, and where do we place that learning? And the last one, again, is looking again at human-centric sensing. So I'll go through these. So in terms of sustainable infrastructures, what we're starting to look at is the impact of, for example, where we place the sensors, the numbers of sensors in a space. What happens if you don't understand the phenomena that you're measuring before you put your sensors out? How can you, what is the iterations that you need to be able to understand the phenomena? Then you can maybe reduce the numbers of sensors that you have out there. All those things. So the work that we've been doing with Turing is the relationship between the data and what we can get from the data and how it can inform the sensor system and vice versa. So we want to be able to diagnose failures in the computer system itself, as well as diagnosing the failures coming in from the data that we're measuring off the physical system. So we want to be able to run those algorithms, and we want to understand how we can push those algorithms right down into the tiny little computer system as well, which means we have less resources used to ship that data, which means the big back-end servers have less data that they can operate on, so it's less complex, but they still have the advantages that they haven't lost the informational content of that data. So we've been looking at that. So we've been looking at, as I said, lightweight approaches to replace some of what's traditional methodologies that typically people would use on a large, say, cloud machine to do that kind of, diagnosis and failure and recovery and identification of faults and so on. We're also looking at mining the stream in real time. So that's looking at the system as it's sending the data through, how we can mine that live as it's coming through, how we can look at motif discovery, feature extraction and visualization have been our particular focus. And again, that's on the continuum from the tiny little node through to the base station and through to the back-end servers. So as I said before, we're looking at many different aspects of that, and we're interfacing that with life cycle analysis as well. The control system is interesting. Control is a subject that has been around since we invented a governor in the Industrial Revolution. So control traditionally it comes from something that the sensors are periodically checking on something, and when there's a deviation, then it issues a form of control. The controller decides on what the type of control action that happens, and that's your typical. But our computer systems can't be doing that. They can't be just periodically sensing and sending when there's no need to and nothing exciting is happening. So what we're looking at is aperiodic control that is not time triggered. In other words, it's looking at event-based control. So only do the sending of the data when there's something interesting has happened. Now, so it will periodically sense, or continuously sense in some cases where we've got energy to do so, but it'll only send data when it needs to. So we have to understand that. Now, so basically what we have is a trade-off there. So we have to basically look at the scheduling of the sensors and the transmission. So that's two different schedules to maintain the stability of the system. The stability of the system under control, whether it's a water system or a precision farm system or a separator or whatever, it depends on that actual system. So one size does not fit all in this particular environment. But what we're doing is we're trying to build protocols that can have parameters that we can slide them to adapt to tailor to the different actual control system under study. Okay? And we've been typically using hybrid system methods to be able to do that. So we've designed two communications protocols so far. The two communications protocols, one is looking at a building-wide communications protocol with reasonably fast sort of Zigbee speeds of data. And the other is looking at LoRa, and we're the first to do that. So we're the first to actually turn LoRa on its head, which has been designed for just sensing and sending, and turn it into a control system, and give the guarantees that the system will be maintained as stable as it operates and changes. And that's taken into account disturbances and so on. So that's what we've been looking at that. Another thing we've been looking at is machine learning generally. We use machine learning to monitor our systems, but also the data coming in from the physical system also needs some sort of, at least machine learning for different reasons. And so we've been looking at different ways of allowing this to happen, given that our system does change over time. The environment it's stuck in is changing over time, and it's continuous data coming in, so you can't just relearn stuff. We can't store histories in our kinds of systems, so we have to understand how we can do learning when we don't have anything to look back on, and so on. So we've been looking at, as I said here, we're looking at sample size, adaptive learning, meta learning, and so on, and new ways of doing reinforcement learning. And our partners in this, some of the applications are, this is a separator, so this ABB have basically given us a challenge and said that we, Imperial, ourselves, could not build a system that would maintain the stability of a separator to the same extent that their wired systems would. And they put their money where their mouth is and give us a separator, so it's being shipped right now. So we've built all the models and so on so that we can actually simulate and play around with our version of that system, and we're hoping to be able to prove them in the real world that we can actually use our rubbish technology to do the same job as their mighty fine technology. And as I said, I work a lot with the water industries to look at things like the sludge systems, the water distribution networks, and so on. How are we for time? We're okay? I have no watch. Oh, that is there. Okay. The last thing is the human-centric sensing, because we can't get away from that, because the humans are a fantastic source of information. But there's a lot of things that we need to take into account. So the physical aspects are, the human's wants and needs, the human's ability to do things, and the fact that if it's a machine that's doing it and it's in their pocket, well, that's the physical world impacting on the actual reading of data, or the human telling us what the data is, and so on. So we've been looking at three aspects. We've been looking at user incentivization. We've been looking at ways of giving the rewards to the participants, but we can't do it like where we can't, for example, decide that that participant in the past has been really faithful because they've always given us accurate data, blah, 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 because we can't really store all that in a lot of our systems. But moreover, we're taking privacy into account here. So all the work we do in this section assumes we want highly, the user wants their privacy to be maximized. So we're maximizing privacy, but at the same time trying to understand whether or not the data coming in from an individual is, it's worth sending up, because are they trustworthy, essentially. So that's the trustworthy reporting. Incentivization, we don't want them lying about what they've done so that they get whatever the reward is. So we have to be able to, use things like mechanism design and so on to try and encourage them not to lie about what they're sending through or the quality they're in. And then finally, we want to be able to evaluate the data so that we can do predictions about where we can get good data, should we need it. And again, in such a way that we're not storing lots of information about individuals. So this is non-trivial to be able to do that. So that's the other thing that we're looking at. So we're coming to an end. I hope I've given you an idea of all the different physical systems and their impact on the kinds of computer systems that I'm building. We don't build them without taking into account that physicality of the system and its environment, and the impacts that, for example, security and so on, and now privacy have in terms of demands on that system. In the end, we hope to have a nice system that works all together and people feel that they can use, and that it actually enhances our environments. And we aren't the first people to think of that. In the 1960s, some of you may have seen this video before, in the 1960s, Richard Brannigan had a poem to this effect, and I thought I would let you see it. Anyway, I hope that was a nice end to my conversation about cyber-physical interactions. Thank you very much.